So as I said, there is no requirement for the grid to be structured, no requirements at all on the grid, in fact. And in CFD applications, of course, you can imagine that most of the geometries are quite complex geometries, and it is advantageous to have the freedom to do a mesh with any shape. By structured, remember what we mean is that we have, if I give an example with 2D, that we have two families of lines, one family approximately vertical, one family approximately horizontal. They don't have to be precisely, when they are precisely vertical and horizontal, we call them Cartesian, but we could have something like, something like that, some sort of skewed mesh, and it would still be structured in the sense that there's only two families of lines in this 2D example, and they only intersect in one point. Now, if I have triangles, that doesn't, if I have, some sort of triangular mesh, that wouldn't match to either of these descriptions. That's what we mean by structured. So we don't require a structured grid in the finite volume method. We do require it in the finite difference method that we've been studying until now. We've actually considered the finite difference method only with uniform distributions of points, a uniform grid where delta x and delta y is always the same for two pairs of points. It is not necessary to do that in the finite difference. We could have, for example, delta x changing to perhaps adapt to some feature of the solution. That's possible to do in finite difference, a non-uniform changing grid. It would also be possible to have a problem in which we perhaps have a curvilinear grid, and we use a coordinate transformation to a square one, and we do all the square one, rectangular grid, and we can do all our finite difference on the rectangular grid and then move back to a curvilinear grid. That is possible. So the finite difference method would allow us that situation as well. We haven't looked into it, but it's possible. It requires, of course, all the additional going back and forth from a curvilinear to a rectangular grid, and there's only so much that you can do with that. You can't have a really complicated grid. You need to have some sort of smooth transformation that goes from one to the other. But in the finite volume method, we don't have any restrictions whatsoever, and the mesh, well, there are implications of accuracy perhaps for something that is an extremely skewed or weird mesh, but in principle there are no restrictions on the formulation that ask you for a particular form of grid. So that makes it very general. It's a very general method in this way, and very flexible. Now, the other thing about the finite volume method, which is important, is that it uses the integral formulations of the conservation laws. Now, in fact, the conservation laws are, in their most native form, integral formulations, and we'll recall a little bit what that means in the next slide. And when we obtain differential equations, we have already gone through a process of a limiting process, and we also have assumed certain smoothness in the solution because we assume them to be differentiable if we're writing differential equations for them, right? Whereas in the integral formulation we don't have to make that assumption, And so if we have solutions which include shocks or discontinuities of other form, then perhaps the integral equation will be more appropriate because we're not making that assumption of smoothness. And another important feature is that it is based on cell-averaged values. Unlike the finite difference method, in the finite difference method, we all our numerical quantities are defined as local values in a point, right? And at the mesh points, as a finite difference approach. In the finite volume approach, we're considering some form of average on a cell, where what I mean by a cell is one of these areas in 2D, volumes in 3D, which are enclosed by our mesh lines. And so the discretization form, unlike the finite difference method, is actually this set of small cells rather than a set of points. Now these small cells are actually the finite volumes that we talk about, where the integral equation, the integral conservation laws are going to be applied. Now, one of the advantages of this is that a conservative discretization is automatically obtained. And we'll discuss this in a moment, a little bit more. What it means to have conservative discretization. Automatically satisfied through the direct use of the integral conservation laws. Okay, so let's clarify what we mean by a conservative discretization. First, recalling what a conservation law is. The variation of the flow quantity, the conserved flow quantity, within a given volume is due to the net effect of two things, some internal sources and the amount of that quantity which is crossing the boundaries. That is, in plain English, what a conservation law is. When we talk about this amount of quantity which is crossing the boundary, by this we mean the fluxes. This is the flux term. So we have sources and fluxes. And the variation of the quantity is due to the sources and fluxes. So if we look at the differential form of a conservation law, you will recall that the fluxes appear exclusively under the gradient operator. We've said this before. So, and also the gradient operator is the only spatial derivative that appears in the equation. So basically, this gives us a way to recognize a conservation law. We just look at the equation and look at the space derivatives and see whether they only appear as a gradient operator. Look at the space derivatives. And can they be grouped in the form of a divergence operator? Maybe when you look at the equation, they're not precisely in that form, but if you do some manipulations, can you group together all of your space derivatives into the gradient operator? If you can, then this is a conservation law, okay? So, of course, in fluid dynamics, all of the flow equations represent conservation laws. And we have said before, if we're writing them in differential form, we require the fluxes to be differentiable. So the differential form requires the fluxes to be differentiable, as I said before. Which is not always satisfied. This is violated, for example, when we have shocks in the flow. There are other forms of discontinuities. You could have a surface or line of discontinuity in the velocity field, which is a slip line, for example, behind a trailing edge, and that could also be a violation of the differentiability. We sometimes forget this. It's important to keep in mind that when we're using the differential form of the equations, we are making this assumption. Sometimes this even may introduce some solutions that wouldn't be possible. So recall the general form of a conservation law. It looks like this. We have the variation of a flow quantity, which let's call it U, in the volume, in a given volume, is let me put the flux terms here, but the variation is due to the net effect of the flux terms, some flux crossing a particular surface, ds, and some form of sources. We usually put them on the right hand side, some sort of volume forces of this quantity. And my omega represents volume here. So note that the variation only depends on the variation of U, only depends on the surface values of the fluxes. Okay? So suppose we divide omega into, just to make it, to make an easy argument, suppose we divide omega, we have omega to be some sort of a quadrilateral like this. Suppose this is our omega, and I'm going to call it AB here, and I'm going to also divide this omega into 3 subvolumes. So just to make them different shape, I'm going to make them different like this. So this is the point C. This point here in the middle is I'm going to call D, and this point here I'm going to call E. So we have a volume omega divided into 3 volumes, omega 1, omega 2, and omega 3, and these are here omega 1, say omega 2, and omega 3. Okay, so now we can write the conservation law for each subvolume. And we would have Well, d dt of the integral in omega 1 of this quantity u d omega plus the integral across the surface for omega 1, I have a, b, c, a, b, c, a, and flux dot the surface normal vector, and I have the sources in omega 1, q d omega. For the second volume, I would have, subvolume, I would have different fluxes. The fluxes will go number 2, so number 2 is d, e, b, d, d, e, b, d, f dot ds, and a source inside omega 2. And finally, in the third volume that I have drawn here, omega 3, the variation of u depends on the fluxes across. For omega 3, we have a, e, dA, f dot ds. ds represents the surface normal vector, and the sources are in omega 3 here. Okay, so we have one equation for each subvolume. We can write the conservation law, and we note now here that in our fluxes, in our flux terms over here, when I'm looking at omega 1, I'm going to draw, I'm going to change colors here to red. I'm going around the surface here in the following way: A, B, C, and back to A. And when I'm looking at omega 2, I'm going DE, so I'm going from D to E, and then I'm going to B, and back down to D. And when I'm looking at omega 3, I am going from A to E, and E to D, and back down to A. So what I want to show you here is that by adding together the three subvolume conservation laws, when summing up the surface integrals, the contribution, if I sum these up, the contribution of all the internal surfaces is always appearing twice, but with opposite sign, and therefore they cancel. And that is a property that is going to be very important for this numerical scheme. So internal surfaces, contribution of internal surfaces, cancel, and thus the numerical scheme is conservative in the way that it treats the flux terms. That is what we mean by a conservative discretization in the finite volume method.